Joyce Lee. Okay, so we're in section 9.4. Joyce, on the back table, we have not only the chapter 9A, which is really our chapter 10A packet. Oh, what just happened? What? I don't know. And we're trying to start notes. The kiddos have already copied down the notes that you just saw a second ago that just disappeared quite literally from before our eyes. My computer said no, I suppose. Let me try again. Okay, let's see if it works this time. Aha! Oh, still not working. Oh, it did work. Haha. Okay, comparison of series. There are two different tests in this one, and Joyce Lee, the calendar online is a little bit wrong. This is going to take 3 days instead of 2, so the board is wrong. Our homework is due on Friday. Never. What? Friday instead of Thursday. Oh, thanks. Look at Sam. He's looking out. Okay. Direct comparison series. Nope, direct comparison has 4 series. If a sub k, the sum of a sub k, the infinite sum of a sub k, and the infinite sum of b sub k are series of positive terms, once again we have a condition, such that each term in a sub k is less than its corresponding term in b sub k, then, and here's the long story short, in each of the questions you are given one series, true? If you want to compare, you have to find a series to compare it to. Which means you have to make up / deduce / figure out a good comparison series. That's where this gets a little bit harder. P.S. This is endeavor number something. Not sure which endeavor it is.
I feel like it's 15, but it could be really off.
That sounds about right.
But I have it written down.
Where's the last one that we wrote?
The last one was the initial test, right?
Yeah, I think so.
That was 4.
Okay.
What was it, PC?
That's true. Did we not mark P series?
And then 16. Just B series would be 15.
Oh yeah, I just wrote it wrong on my page. That's a struggle. So he was 15. Okay, all better. He is number 16. Okay, let's come back in. But in order to do this test, the direct comparison test, one series has to be always bigger or always smaller, depending on what you're looking at. Now, here's a quick heads up. If we are trying to deduce, or if we are trying to figure out the convergence or divergence of a series, then the one that we are looking at, is the second in each of these phrases. Okay? Because we're looking at the then. We're trying to figure out the conclusion. So, then the smaller converges, or then the bigger converges. Which means we're looking at the one that we're trying to figure out, the one that we're trying to use is going to be this first one, the smaller that diverges or the bigger that converges. So, one more time. If or when we look at a question, this test gives us the answer if we think of the one that we are trying to figure out the convergence or divergence as the second in this statement, okay? So the ifs are the ones that we should be able to easily do, and then based on their conclusion, then we are able to answer ours that we are looking at. This one, use this test as a last resort. It's kind of awkward because we're covering it first in the sense of the two comparison tests. Other tests are usually easier to apply, not always. And once again, this test only applies to series of positive terms. That's pretty stinking important. Once again, it can't be alternating. It can't be totally negative. What on earth is going on with my little down here? Okay, I'm kind of reiterating a major point about this test. Number 2, this test, I think, can be explained a little bit easier with what I've written down below. To converge, in order for what I'm looking at to converge, I have to squeeze it in, or if it diverges, I have to push it out. Here's what I mean. Ready? Let's say this is the sequence that we're trying to figure out the convergence of. Oh, everybody look at me. Check. Look at me. Okay. If this is the one I'm trying to figure out, okay? Let's say this is a number line. So then on a number line, where are the smaller numbers or the more negative numbers? For you guys. That way, right? And for you guys, this way are the bigger numbers, right? Okay. So let's say we can think about, or we know the convergence or divergence of a bigger series. Okay, always bigger. Every single term is bigger than this one. So we can say it's greater, whatever, whatever, whatever. If the bigger one that we can figure out whether it converges or diverges, if it converges, what's it going to do? It's going to squeeze this one in the sense that whatever it converges to, it's going to squeeze this one together, and it's going to do the squeeze theorem. Okay? That one converges also, right? If the bigger one diverges, do I know anything about him? No. Maybe he diverges, maybe he converges. I don't know. So the bigger can only squeeze in, the bigger can only show convergence. If the bigger diverges, it didn't help. If I look at a smaller series, if the smaller converges, do I know anything about him? No, maybe he converges, maybe he diverges, I don't know. But if I can find a smaller that diverges, what can I tell? That guy diverges also. Does that make sense? So, with the direct comparison test, you can think BC, if the bigger converges, my series converges. If the smaller diverges, my series diverges. But if the bigger diverges, know nothing. If the smaller converges, I know nothing.
We're up to speed.
Okay? Up to speed, that's scary.
No, the reference to Big Panda. They were.
So, quick note. One other thing, remember the integral test? Remember how some series you guys thought you couldn't use the integral test on because, say, it increased at first and then decreased? And we had a way of working around that? By separating the first 1 or 2 or 3 terms and then looking at the rest of the series and figure out the rest of the series, convergence or divergence plus constants, it still converges or still diverges. Same thing here. With the direct comparison test, there is going to possibly be a kink in the system. And a kink in the system is going to be, technically, the convergence of a series is not dependent on the first several terms. This is what allowed us to split up the integral test. Which means, for the direct comparison as well, we can also modify the test to require only that a sub n is less than or equal to b sub n for all terms past a certain point. Or b sub n is greater than or equal to a sub n for all terms past a certain point. So is it true that one series has to be bigger than the other for all the terms? No. The first or second or third, the first 5 terms maybe won't be bigger. But as long as eventually it switches and says, okay, it's going to be bigger from here on out, what we're caring about is as we go to infinity, right? The infinite partial sum. The partial sum, the limit as n goes to infinity, either way. The limit of the partial sums, that's the best way of saying that statement. We don't care about the first few, even the first several. We care about as we go to infinity what's going on. Does that kind of make sense, guys? So the same thing we were able to do with the integral test, we're able to do with the direct comparison as well. At the first couple terms, the one isn't bigger than the other, but then it switches, then I'm good. And I just have to kind of state that in the sense of separating the series and then looking at the two and making my conclusion based thereupon. And quick heads up, lo siento, this is technically not page 612 of our book. It's page 612 of the book you guys will have a copy of. But it's still a good statement because it's what allows us to work with special cases of the integral test and the comparison. Now there are technically 2 comparison tests. For sake of time, when referring to the direct comparison test, let's just say comparison. And there's a second one, it's called the limit comparison. Then we will specify limit comparison instead. So we'll make this the original, and then the limit one we'll add the extra qualifier, the extra adjective on. Alright, here we go in the notes packet. Which of course you could be writing in your composition book, or you can just be working with us. Let's go through all 4 of our tests that we have so far. So, what's the very first test we should usually try? Because if it works, we can quickly stop. Nth term. However, struggle. What's the limit as n goes to infinity of?
0.
That doesn't work. We know nothing. Number 2, geometric. But let's get the first few terms just in case, so we can see what's going on for maybe some of the future terms. So plugging in 1, plugging in 2, plugging in 3, Okay, we know it's not geometric, right? So forget him. How about P-series is easier than an integral test, right?
Yeah, pieces are inanimate because it will be a what's it called? Variable to a constant, but this is a constant to a variable.
True. Because you're already saying this isn't an n squared, this is a 2 to the n, so it's the wrong orientation. It's almost a geometric except for the plus 1, right? The plus 1 kind of messes us up. So P-series doesn't apply because n is not being raised to a power. If this is exponential, not power. Because n is in the exponent. Number 4 says integral test. Well, fine. In the first sections 9.1 and 9.3, when things got hard, we started taking integrals, right? Now, if I were you, I would not write what I'm about to show. Because we would compare to. Question for kids. How would I go about integrating 1 over 2 to the n plus 1? Or 1 over 2 to the x plus 1? You said? No, because then I would need another 2 to the x, 1 over, no, ln of 2, right?
So,
Partial fractions? No. Arctrig? Definitely not.
why can't we do partial fractions?
Because I can't factor. Anything? No! So, stink. Question, what looks a lot like this series and would be easier to use the nth term geometric P-series or integral test on? It's very close.
Someone
1 over 2.
1 over 2 to the n.
James.
1 over 2 to the n. So what if we compare, hold on, we have to figure out how does 1 over 2 to the n compare to what we have? What's 1 over 2 to the n, smaller or bigger? Why is it smaller?
Oh, so it's bigger.
So it's bigger, but why? Who has the bigger denominator?
Oh.
Sorry. So 1 over 2 to the n has the, right? 1 over 2 to the n has this smaller denominator, which means the bigger number. Wait, from the get-go? Double check it. 1 over 2 to the n, that'd be 1/2 plus 1/4 plus 1/8. Is it bigger? From the very beginning? Okay, then we're good. So we can say this guy is our bigger, true? So what can we say about our bigger? He better be,
Conversion.
the bigger better be converging. BC, right? Well, let's check it. What do we know about 1 over 2 to the n?
It converges to converges to something like that. Converge to.
We're only going to be able to make a conclusion if we know that the bigger converges, right? So hold on, we got to go think about 1 over 2 to the n. What do we know about it?
It's a geometric series.
It's geometric and r is equal to,
1/2.
which means bigger converges, right? Are we good? All right, so let's finish our statement and say since the bigger converges,
Can you just try CLNB? Even on AP or
remember I haven't necessarily seen a long answer where you do have to state your entire rationale. But we'll keep our eyes open when we get to practice problems, okay? Dun, 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 dun. Does that make sense? That little plus 1, he was a stinker. Except if we took him away and used the direct comparison test, what? Everything turns turns out quite alright. So you guys go ahead and start thinking about number 2. Nth term, nope, limit is 0. Geometric, no. P-series, no. Integral test. While you guys ponder, I'm gonna start writing terms.
No, we can do the integral test. We done this one before.
Okay. How would you do the integral test?
You pull out the square root of n, and you take the root of square root of plus 1, not the 1 is not in the square root, and it'll be 1 over 2 square root of n. The 2 stays, the square root of n becomes du. And it's 1 over u. This was like 100 pounds, I think.
Because we also combine the powers.
We were multiplying.
Oh, yeah.
So we could go ahead and factor out the root n like Gerardo was saying. So it's not that integral test is necessarily impossible. Maybe there's an easier way. If you factor out the root n as he was saying, you would have root n plus 1. U is equal to root n plus 1. You have to do some u sub. Watching out for du, it's going to be a little bit off. And then take the limit, which sounds fun and all. However, since we do have completely positive terms, is there a series we could compare to that is similar but easier to deal with? What'd you see, Jay? 3 over n plus n? Okay. Let's check it out.
Can we rewrite it as 3 over 2n?
So what would be the comparison between, here's our compare series. Did I do it in black or red before? Oh, I did it red. Alright, so if we have 3 over 2n, how does that compare to our series that we're checking out right now, which is
What's it?
It's going to be smaller.
why?
Because the denominator is bigger.
Why am I putting or equal to? Hold on, check it. Wait, on our test, is it allowed to be or equal to? Oh, we don't actually show.
We actually show.
No, we just have bigger or smaller.
But I get to do on the other. That way. It's less than 2. No, yes.
Less than or equal to should be alright. Because it only starts off or equal to, and technically we could separate that term, right, and go for all the rest. Because this one we'd have 3 over 2 plus 3 over 4 plus 3 over, hey, our second full n is always going to be bigger than root n for n greater than 1. Does that make sense? 2 is greater than root 2, 3 is greater than root 3, etc., etc., etc. So we can go ahead and say, okay, so we're looking at currently a smaller series, right? What do we know about the smaller series? Nth term, nope, doesn't work, 0. Geometric, 3 halves, 3/4, 3/6, nope, it doesn't work. Not geometric. How about p-series? How does that one?
Because n
It's
one.
in diversion.
We can say p-series means diverges since p equals 1, right? To converge, p has to be greater than 1, true? So we have s and we have d, are we good? The smaller is diverging, so it's going to push out the other as well. So therefore we can make our conclusion and say, ha-ha, by the comparison test. Since the smaller, which is the one that we chose,
Is it even possible if we accidentally pick the bigger and it doesn't work out, so we have to check the smaller?
all depends on how wisely you choose.
Why is the luck?
I'm sure we'll be able to get it. I'll just be able to see. Like when you were doing the test and you were doing the other test, you were able to see which ones worked for which one.
You get a feel for when they're helpful or not.
Definitely tell them it's geometric. Definitely tell them we can consider that a form of choosing zero.
And that's also going to help you in choosing, right? Because if you know what's easy to figure out geometric or what's easy to figure out p-series, those are the ones that we're trying to compare to. Dun 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 dun. You guys checking out the next one already? This one's not pretty, right? Sine squared of 1, sine squared of 2, sine squared of 3. However, sine does go in between 1 and -1, but there's no squeeze theorem test necessarily. But we do have the comparison test, so let's figure out what we got.
But the sine squared only goes to 0.
Hmm?
The sine squared only goes to 0.
But we have no squeeze theorem for conversion tests, right? But we can say the limit is 0. We don't have to. So we can find the limit of the sequence, but not of the sum.
Does that mean that we know that it's always going to be positive?
It's squared. Sine is squared. So it's always going to be positive. And then 2 to the power is always going to be positive, yeah. So we know that these are always positive. We haven't explicitly been checking that. We probably should have. But the nice thing is we were writing out the terms, so we were able to see this, right? So a sub k is always greater than 0. A sub k is always greater than 0. And on this one, since we have a squared over an exponential, a sub k, once again, is always greater than 0. Okay. Let's come on back to the problem here. Anybody figure out something we should compare it to? How about -1 over 2 to the n? Now wait a minute.
This doesn't need to be positive.
Let's check our test. Is that even allowed, first of all? A sub k and b sub k are series with positive terms. Well, that doesn't work, does it? Okay, bummer. Let's take out the -1. And why would -1 not be useful anyway? Even though sine goes between 1 and -1, sine squared goes between 0 and 1. Okay, let's do 0.
Yeah.
Wouldn't that be lower?
I mean, always.
Uh-huh. So it'd be smaller, and it converges, because it's just 0 plus 0 plus 0 plus 0. Oh, does smaller converging mean anything? Okay, so we're going to not use 0, but what can we use instead? Now we know that's going to be always bigger than, right? Bigger than or equal to? Because sine only goes up to 1. So then all the other ones are going to be smaller than 1 up top. So we can say we have the bigger. And what have we already figured out about this guy? Had you use him a couple times?
He converges.
Because he's a geoseries, right? And r is equal to 1/2. So therefore it converges. So are we good? Oh, yes, indeed we are.
What is that arrow with the equal sign? Therefore.
This implies. You guys figured out what's going to be the hardest on this? Yeah.
Finding the right series to use.
Finding the right series to use in order to compare, true. Are there strategies? Yes. Sometimes it's looking to say, hey, who looks like him but is easier? Sometimes it's thinking like the squeeze theorem, what does sine squared go in between, and then trying to pick something smaller. Oh, it doesn't really work. Bigger? All right, that works. But choosing the series is where it gets complicated, which is why back here in the test you guys might not have really thought about it much. But it does say other tests are usually easier to apply because this is the one that forces you to be creative to choose. Does that make sense? So still good to practice because sometimes it's basically the only way or the easiest way, but not always. Ooh, this looks fun. What are these guys? Telescoping series. Telescoping series. They're a special type of series that sometimes occur. As you guys notice, they're not all positive terms though, right? We have positives and negatives. And by nature of the series, when you try to expand it, you start to see quite a special pattern. You start to see quite a special pattern. In that, if we were to start putting these partial sums together, what would you guys notice? With B2, what happens? What else is going to cancel out? So for the second special term, for the first partial sum, it would just be B1 minus B2. Second partial sum would be B1 minus B3. Third partial sum would be B1 minus B4. Fourth partial sum, B1 minus B5. Do you guys see why they're saying the nth partial sum is B1 minus B sub n plus 1? Wherever we are, that term is going to cancel, and the next term is going to be the only thing remaining. And this leads us to, well, that talks about the nth partial sum. A telescoping series will converge if and only if B sub n approaches a finite number as n approaches infinity. And if B sub n does approach a finite number, then we can say, as long as it converges, not only do we know that it converges, but we also know its infinite sum. Wait, what was the only other type of series that we've figured out or known how to find the infinite sum if it converged? Geometric. So now we have a second one, not only geometric, but also telescopic.
How do you call it telescope?
Think of a telescope. So when we're finding terms, think of those old power telescopes where you would pull it apart. You would pull and it would expand. But then, ultimately, when you push it back together, all the in-between disappears. Same thing here. In the sense of all the in-between terms, however far you are, all the in-between terms cancel out. I think that's ultimate where it came from.
You should call it the pirate series. That'd be cool.
You can try that, but I'm pretty sure other math teachers would not